All right, let's jump right in. Today we're going to tackle a classic mechanics problem, one from the legendary Irodov problem book. It's number 1.94, and this one has a reputation for tripping people up. But don't worry, we're going to break it down piece by piece and make it make sense.
Okay, so let's read the official problem. When you first see this, your brain might just go, whoa, that's a lot. You've got a particle, a cylinder, some initial velocity, an angle, and it's asking for a force. It's really easy to get lost in all the words. But here's the thing about problems like this. They are not as scary as they look. Once you have a clear strategy, all that complexity just kind of melts away. The real trick isn't about memorizing a bunch of formulas. It's about learning how to think about the problem. So before you even think about writing down an equation, stop. The most important thing you can do is come up with a game plan. You need a roadmap that's going to take you from this confusing word problem straight to the final answer. So here's our game plan. It's a simple 3-step attack that works for tons of problems. First, we're just going to picture what's actually happening. Second, we'll break the tricky motion down into much simpler pieces. And then finally, we'll bring in the big guns, Newton's laws, and apply them to the right piece of the puzzle. All right, step 2, deconstructing the motion. This right here is where we have our first big aha moment. We've got this one particle moving in what seems like a complicated spiral, but we can be clever about it.
The real key, the thing that unlocks this entire problem, is realizing that the initial velocity is doing two completely separate things at the same time. It's not one complex motion. No, it's two simple motions, just happening to occur simultaneously.
So let's just bust out some basic trig. We can split that velocity vector into its two components. We've got a horizontal part, v0 cosine alpha, and that's the part that makes the particle go around the cylinder. Then you've got the vertical part, v0 sine alpha, which makes it go up or down the cylinder. And what's really cool here is how cleanly we can separate these two. I mean, they are completely independent. The vertical motion is just the particle fighting against gravity, moving up and down. The horizontal motion is the particle going in a circle because the wall is pushing on it. And since the surface is smooth, that's a key word, there's no friction to link them. They literally don't care about each other. So let me ask you a question. We're looking for the force the particle exerts on the wall. Which of these two motions, the up and down one or the round and round one, is actually responsible for that force?
You got it. It's the horizontal motion. The vertical motion is in a whole different dimension, just dealing with gravity. It's the circular horizontal motion that needs the wall to push on the particle to make it turn. So from here on out, we can totally ignore the vertical part and just focus on the circle.
I mean, think about it. If you were a bird flying directly over the cylinder and looking straight down, you wouldn't even see it moving up or down. All you'd see is a little particle going around in a perfect circle of radius r. And because there's no friction, its speed is constant. It's just that v0 cosine alpha. Now, things don't just decide to move in circles, right? Inertia says an object wants to go in a straight line, so there must be some force that's constantly yanking it toward the center of the cylinder, forcing it to keep turning. What is that force?
And that force is what we call the normal force. Don't let the name confuse you. It's just the physical push from the cylinder wall itself. It's the wall pushing back on the particle, and it always points directly towards the center of the circle.
Okay, big warning sign here. This is a trap that so many students fall into. They draw a force diagram, and they add a new arrow for centripetal force. No, no, no. Centripetal force isn't a new force. It's a job description. It's the net force that points to the center. And in our case, the only force pointing to the center is the normal force. So the normal force gets the job. So here's where it all comes together. We pull out the big gun, Newton's second law, F equals ma. The net force pointing to the center, which we now know is just the normal force, N, must be equal to the mass times the centripetal acceleration, which is just v squared over r. And hey, we already figured out the specific velocity for this circular motion. It's not the full v0, remember? It's only the horizontal part, v0 cosine alpha. So we just take that and plug it right into our equation for v. We just clean this up a little bit, square the terms inside the parentheses, and bam, there it is. That's our expression for the normal force. That's the force that the wall is pushing on the particle with. But wait, hang on. Let's read the question one last time. It asks for the force the particle exerts on the wall. We found the force the wall exerts on the particle. Well, thanks to Newton's third law, we know that for every action, there's an equal and opposite reaction. The forces are a pair, so their magnitudes are exactly the same. Phew! So, we've got an equation. We're done, right? Nope, not yet. A good physicist never just stops at the equation. You gotta do a sanity check. Does this answer actually make sense? Does it behave the way our intuition tells us it should?
Let's poke at this formula a bit. Let's try two extreme cases that are easy to picture. What if we shoot the particle perfectly horizontally? That means our angle alpha is 0. And what if we shoot it straight up? That means alpha is 90 degrees.
And look at that, it works perfectly. If the angle is 0, cosine of 0 is 1, and we get the maximum force, which is the standard formula you already know for circular motion. Makes sense. If the angle is 90, cosine of 90 is 0, so the force is 0. Of course, if you shoot it straight up, it just slides along the wall. It never pushes against it at all. Our formula holds up.
And that's really all there is to it. We took a problem that looked really intimidating, and by following a simple plan, we turned it into something totally intuitive. Now, for a little extra credit, think about this. Our whole analysis depended on that word smooth. What do you think would change if we added friction to the cylinder wall? How would that mess things up?